Hi everyone. So in this video I'm going to go over the practice quiz 4 for Organic 2 Lab. It says, what is the major organic product of the following Grignard reaction? Circle your answer. So in this case we have a ketone reacting with methyl Grignard first in the presence of diethyl ether, and then it's acidified. So generally speaking, you could just remember that Grignards and ketones form alcohols. Okay, but I want to talk a little bit more detail, and the mechanism is down a few questions from now, but I want to talk a little bit of detail about the mechanism. So because of this carbonyl carbon, okay, because it's double bonded to the oxygen, we could write a resonance form where this lone pair goes up here, and this is minus, and this is plus. Said another way, this carbonyl carbon is partially positive. This carbon, because it's attached to a magnesium, is partially negative. So this partially negative carbon attacks the carbonyl carbon, and this moves up like this. So effectively, this carbon is acting as the nucleophile, and this carbon is acting as the electrophile. Then this moves up here. Then you have a minus charge on the oxygen, and then you just have a counter ion, which is just MgBr. So this is minus and this is plus. And this is what you would form in the first step. However, in the second step, we acidify, and this molecule is a pretty strong base. So when you add acid, you protonate here like this. Note that the oxygen has moved, but that doesn't matter, right? Because this bond has free rotation. So if we look here, this carbon becomes an alcohol. It has a new methyl group attached to it. That's from the Grignard. And it still has this CH2CH3, the CH2CH3, which is the ethyl group, which is right there. So this is your answer. And I should have mentioned the ring just goes along for the ride, so does the ethyl group. All right, question 2 says, in the Grignard reaction, the glassware used for the reaction and the solvent must be dry before the reaction, must be dry for the reaction to work. What organic product is formed when the Grignard reagent below reacts with water? Circle your answer. Okay, so there's only two reasonable answers here. Okay, one reasonable answer is CH4, and one reasonable answer is CH3OH. This isn't organic, right? Doesn't contain a carbon, and this somehow contains two carbons. All right, and this only contains one. So let's look at water, and I'm going to write water like this. So if you've seen the previous question, we talked about the Grignard reagent, in this case methyl Grignard, and we talked about how this carbon is partially negative because it's attached to the metal magnesium. So since this carbon is partially negative, we need to decide, does it go after H or does it go after O? If it goes after H, we'll make this. If it goes after O, we'll make this. So which will this go after if this is partially negative? Well, if we look at this, water, the oxygen is partially negative and the hydrogen is partially positive. This one's partially positive too, but it doesn't matter because it only needs one. So this negatively charged carbon, partially negatively charged carbon, is going to go after the partially positively charged hydrogen, and that's going to break off like that. What is the inorganic product? Or excuse me, the organic product? The organic product is CH4, because instead of CH3, we're not going to have CH4. The inorganic product is MgBrOH, but it's not asking about that. It's asking us for the organic product. All right, so in the previous two questions, we've alluded to this one, which is ultimately the mechanism for the Grignard reaction. It says, write the mechanism for the formation of the major organic product of the Grignard reaction below. So as we've talked about, this is partially negative, and this carbonyl carbon is partially positive. So this carbon acts as the nucleophile, and it attacks this partially positive carbonyl carbon, and then this double bond becomes another lone pair on oxygen. What we end up with in the intermediate stage of the mechanism is 5-membered ring. Nothing changes with it. Sorry, that's not a 5-membered ring. Okay, 5-membered ring attached to the carbon, which is this carbon right here, which is now attached to an O, which now has 3 lone pairs and a negative charge because it now has an extra electron around it. You'd share with these. Now it has both, so now it's got an extra electron, so it's minus. We have the new CH3 from the Grignard reagent right here, now attached here. And then over here, we just have CH2, CH3, which is just this ethyl group right here, just goes along for the ride. So this ring isn't doing anything. This ethyl group isn't doing anything, but we added this CH3 to the carbonyl carbon, and now this has a minus charge. If you want to write the byproduct, it's just MgBr with the plus charge, okay, or the counter ion, if you will, at this point. So this is basically what you have. Now, this is a pretty strong base because it's effectively a deprotonated alcohol. So we add some kind of acid, H3O plus. This is going to grab one of those H's. So the oxygen acts as a nucleophile and grabs one of those H's. And what we end up with is this 5-membered ring. That's a 5-membered ring, okay, bonded to the C, bonded to the OH, like that, and then bonded to the CH2, CH3, and then bonded to a CH3 down here. Okay, now what is left with this? You're going to end up with some magnesium salt. All right, if you want to do MgBrOH, it could be that. It could be MgBr2. It's just some magnesium salt that are going to form as the byproduct here. But the important thing is that we protonate this alcoholate with this because this is a pretty strong base, and we end up with an alcohol. So this Grignard adds a methyl group because it's methyl Grignard and converts the carbonyl or the ketone into an alcohol. All right, question 4 says, a student completed the Grignard reaction shown below. The product was isolated and the following IR spectrum was collected. So just to remind ourselves of what the product is, which we talked about in the previous several questions. This is the product of the reaction, okay? So we get the alcohol. It says, does the IR spectrum collected support the conclusion that the product of this reaction is pure? Does not contain any starting material. What is the major IR spectrum evidence that supports this conclusion? So we need to look at the difference between the starting material and the product. And if you notice, the major difference is this one has a carbonyl carbon, which should have a peak around 1700 centimeters minus 1. And this one has an OH, which should be a broad peak around 33, 3400, something like that. So this right here is the OH, and this right here, if you will, something like that, okay, is where you would see a C double bond O, but there isn't one. So now we just need to see which one is the better answer. Is it the lack of the OH or is it the C double bond O? And it says, yes, there is no C double bond O peak around 1700. That's true. All right, we've gotten rid of the starting material because we don't have a C double bond O. Yes, there is no CH aromatic peak around 3100. I'm not sure how that helps us because this is not aromatic to begin with. No, there is no OH peak around 3500. No, there is an OH peak around 3500, and that tells us that it is pure, not no. And then it says no, there is no C double bond O peak around 1700. So the IR spectrum does support the conclusion that this is not containing starting material. So it's yes, not no, and it's because there's no C double bond O peak here. I will note that in real life, this OH peak can be a little bit tricky because you acidify this with water. So sometimes the OH could come from the water when you're acidifying. You're not actually acidifying with water, but when you add aqueous acid, there's water present. So that's basically that. All right, so we're at the end of organic 2, so I'm not going to spend a lot of time on formal charges. All right, it says, what are the formal charges of the star atoms from left to right? Circle your answer. So the first thing you need to remember is that these all have octets. So this one is shown to have 1, 2, 3 bonds to carbons. So it must have one lone pair to fill its octet. Nitrogen is a 5A element. It wants to have 5 valence electrons around it. How many does it have? 1, 2, 3, 4, 5. Count the dots as 1, count the dashes as 1. Why do we count the dashes as 1? This is 2 electrons. 1 belongs to carbon, 1 belongs to nitrogen. 1 belongs to this carbon, 1 belongs to the nitrogen. So 1, 2, 3, 4, 5. Nitrogen wants 5. It's a 5A element, and it has 5, so it's neutral. Let's look at this carbon. This carbon is shown with 1, 2, 3 bonds. So the carbon has 3 bonds. So I'm going to add a sentence here that says the carbons do not have an octet, because that will make this make more sense. So the nitrogens and the oxygens will have octets, but not the carbons. So if we look here, this carbon has 1, 2, 3 bonds. Carbon is a 4A element, and as you know, it likes to have 4 electrons around it. You've seen that a lot in organic chemistry. And this one only has 1, 2, 3. It's missing an electron, so therefore it has a +1 charge. Let's look at oxygen here. Oxygen has 1, 2, 3 bonds, so therefore it must have a lone pair. So oxygen has 3 bonds in a lone pair. Oxygen's a 6A element, so it likes to have 6 electrons around it. It has 1, 2, 3, 4, 5. It's again missing an electron, so it is +1. So the answer here is 0, +1, and +1. Number 6 says, which of the following methods could be used in lab to keep water from reacting with the Grignard reagent before the product could be formed? Circle only one answer. Alright, heating the glassware in the oven before the reaction is started. This is exactly why we heat glassware. Alright, it's to remove the water. Even if you can't see that it's wet, small amounts of water do condense on the glass. Washing glassware with water and acetone after removing it from the oven. That's a bad idea. Okay, you don't want to wash with water after you take it out of the oven. It should be pretty clean after you put it in the oven, before you put it in the oven, so then after you've gotten rid of the water. Using anhydrous diethyl ether as a solvent for the reaction. That's important. Anhydrous means free from water, or at least relatively free from water. Adding 6 molar HCl to the 3-neck flask before you start the reaction. Again, 6 molar HCl is a water-based thing. Okay, it's mostly water, and then 6 molar of HCl, but the solvent there is water. You don't want to add water. You actually don't want to add HCl to a Grignard anyway, because if water will protonate a Grignard, HCl will really protonate a Grignard, as we talked about back in question 3. So in this case, if we look here, A and C are your 2 correct answers. So the answer E is the best answer. Alright, so we have everybody's favorite, a safety question. It says, in the Grignard reaction procedure, sodium bicarbonate solution is used in a liquid-liquid extraction technique to neutralize hydrochloric acid from the reaction mixture and isolate the product. If you do not vent the gas formed during the extraction, pressure could build up and liquid could be splashed onto your face and goggles. What should you do if this happens while you're working in the lab? So when you mix hydrochloric acid and sodium bicarbonate, it makes carbon dioxide and pressure, and as it says, it can splash stuff into people's face. Alright, FaceTime your friends and ask them what to do. That's probably not the best idea, okay, in a dangerous situation. Do nothing. Chemicals aren't dangerous. Again, probably not the best idea. Inform the TA and use the eye wash station or sink to wash off any chemicals for at least 15 minutes. Seek medical attention as necessary, which is obviously the correct answer. And then run out into the hallway without telling anyone where you're going is obviously not the right answer. Okay, so a pretty straightforward question. And at this point in Organic 2, I know you're all familiar with the safety procedures. Alright, so the last question is quite a long one. It says there are several parts of this question. Be sure to answer all parts of the questions to be able to earn full credit. So the student performs a Grignard reaction using the procedure like the one used in the course. The crude solid product is isolated after liquid-liquid extraction procedure to remove excess acid from the Grignard mixture, and the solvent is removed by evaporation. The reaction was completed, and the Grignard reagent as a limiting reagent and excess ketone in the starting material. The student uses column chromatography to isolate the product from the excess starting material using 5% ethyl acetate and hexanes as the mobile phase and silica gel as the stationary phase. The column chromatography results are monitored by TLC with silica gel as the stationary phase. So it says, the first question, and there's a bunch, A, B, and C. It says, compare the relative polarity of the product to the starting material. Which compound is more polar? So this is our starting material in this question. This is our ketone. Recall from the previous previous questions, that the product is, we add the methyl and change this into an OH, and then the ethyl group and the pentane ring just go along for the ride. it asks us which of these two compounds are more polar. Well, this one has OH, this one just has the carbonyl. So this one is less polar. Okay, the ketone is less polar, and the alcohol is more polar. And the reason for that is this one has an OH, and this one has a carbonyl. So that makes this one more polar than this one. The next question is another long one. It says, the student spots a solution of starting material, a solution of the product, and a solution of the crude product onto a TLC plate and elutes the plate using 5% ethyl acetate and hexanes, but forgot what they spotted at locations A, B, and C. The TLC below shows the results visualized using a UV lamp. Label the spots at locations A, B, and C with starting material, product, and crude product. Why does one compound move up further up the plate than the other? So we kind of need to answer the last part first, because then that'll help us to be able to label these things. So what we need to remember here is that ethyl acetate in hexanes is a nonpolar mobile phase. So the nonpolar mobile phase is flowing through this TLC plate. The silica gel, which is the stuff on top of the TLC plate, is very polar. So if compounds are polar, they're going to stick to the silica gel and they're going to move through the silica gel relatively slowly. If compounds are less polar, they're going to stick to the silica gel less and they're going to move through the silica gel more quickly. So since compound A is sticking more because it doesn't move as far or has a smaller RF than compound B, then we know that compound A is more polar than compound B. Said another way, we know that compound A is our product and compound B is our starting material. Again, because the product has the OH and it's more polar, as we just talked about, and the starting material has less polarity because it's a ketone and not an alcohol, so therefore it moves further. Then finally, the crude product has to be the one with the two spots. So whichever one has two spots has to be the crude product because it has both product and starting material in it. Pure product has one spot, pure starting material has one spot, crude product has both spots. Last one, which is along the same lines of what we just did. The student then runs column chromatography experiment and collects 9 equal volume fractions from the column. Each fraction below was spotted on TLC and the fractions were labeled 1 to 9 in the results below. So if we look here, okay, because these RFs approximately correspond with these, or maybe even exactly correspond with these, we can tell that these fractions here contain the less polar starting material, and these fractions here contain the more polar product, and fraction 9 doesn't contain anything because it's just empty. Okay, so it says list the fraction numbers that contain the starting material. Well, the ones that contain the starting material, sorry, I should have mentioned that 1 is also empty, are 2, 3, 4, and 5. So I'm just going to write 2 to 5. Okay. List the fraction numbers that contain the product, which would be your 5, 6, 7, and 8. So I'm just going to write 5 to 8. And it says which fraction should be combined to isolate pure starting material. So in this case, you would want to not use fraction 5 because fraction 5 contains a mixture, but fractions 2 through 4 contain pure starting material, where fractions 6 to 8 contain pure product, if this said pure product. All right, so this is how we can analyze the TLC plates. Notice that the RFs are the same, so we can use this as kind of a test to know which are starting materials and what are our products here. So I hope that gives you an idea of what's going on in this reaction. I also hope it's clear that you really need to know this reaction, because if you don't know this reaction, it's going to be hard to answer all of these questions. If you don't know what the product is, how are you going to decide which is more or less polar? Okay, so that is basically that. Thanks for watching.